Wasserstoffaktien stehen nach wie vor im Hauptfokus vieler Anleger und auch die Regierung ist umgeschwenkt. Sie will sich nicht vorwerfen lassen, den Wasserstoff als Energieträger der Zukunft verschlafen. Und zwei Unternehmen profitieren davon in ganz besonderer Weise. Wasserstoffaktien stehen nach wie vor im Hauptfokus vieler Anleger und auch die Regierung ist umgeschwenkt.
This fluid simulator is what we're going to build to this series. And once it is ready to go, we study all kinds of fluid dynamical phenomena. Familiar things like lift and drag, but also more unfamiliar things like vortex shedding or pressure-velocity interplay. And there's a very good reason why we don't just pick any of the ready-made software tools. Partly, it comes in handy, we dive into the fundamentals anyway, so why not directly applying what we learn? But more importantly, building it on our own makes us also believe in it. Not just learning concepts and equations, but really seeing where they come from and how they come into play. That's what makes a difference, and we won't miss out on that opportunity. And to get all this going, we start at the subatomic level with fundamentals. Pick any of the ready-made software tools. Partly, it comes in handy, we dive into the fundamentals anyway, so why not directly applying what we learn? But more importantly, building it on our own makes us also believe in it. Not just learning concepts and equations, but really seeing where they come from and how they come into play. That's what makes a difference, and we won't miss out on that opportunity. And to get all this going, we start at the subatomic level that underlines molecular interactions. We use then different approaches to reduce the problem's complexity. In particular, we average out the molecules by establishing the fluid as a continuous field. This continuum is then discretized spatially and temporally, whatever that will mean, and we wrap it all up with the proper boundary treatment. Once we really understand the simulator, we can rely on it for answering any upcoming question. And a super nice benefit of having our own simulator is that we have full control of it, meaning we can actively manipulate the physics and see how phenomena are inherently linked to it. But first things first. To get the mathematical foundation right, we have to dive into fields like computational fluid dynamics, or CFD for short. And CFD is one of those topics. It likes to come with the notion of being unsettling. But whenever you feel overwhelmed, it is a good idea to step back and appreciate that all can be broken down into a few core ideas, and we will uncover all of them step by step in this series. In this first part, we focus on the microscopic foundation that really justifies all the macroscopic implementations of fluid simulation. So my primary goal here is that by the end of this video, you will have a clear understanding of the microscopic perspective of fluid dynamics, and by the end of this series, you will have a good sense of fluid simulations in general. Alright, let's dive in. I bet all of you have a certain idea of how fluids work. Maybe you think of it in terms of discrete colliding particles, or in terms of a continuous flowing medium. To get on the same page, we start off by aligning our perspectives of fluids. They are all useful, but some are more useful depending on the context. Here's what I mean. The central theme underlying simulating flutes is reducing information in every possible way. The reason is simply we can't just process all the raw information that is out there. So before we even start simulating anything, let's get a rough idea of the multitude of information we are dealing with. If we are going to represent all the molecules that make up the flute on a computer, two things show up immediately. A, there are simply too many of them, not just a bit too much, but overwhelmingly too much. And B, there's information we would like to know, but rather statistically, or maybe not at all. Take the rotation of a molecule. Think about it. Do you expect a significant offset, say in lift, if this particular molecule is rotated differently? This right here. Or take the location of the molecules. What matters in the end are the average states of larger portions of them. And given all that, modeling subatomic mechanisms on a quantum level for each molecule would be way off the charts. At least when we are interested in quantities of a more global character, like net lift force for instance. Okay, I think we can all agree on that we have to get rid of a lot of this information. But how exactly? How do we emphasize mathematically what's relevant for us and average out the rest we don't care about? Well, there's not the correct way. The approach we will take consists of several layers or modules, but these can be swapped by alternatives as needed. And this right here is important. Building a simulation in a modular way means giving structure. We will use a lot of these tools in future series, and a structured perspective will pay off. Okay, to really build it from ground up, let's get clear about a good starting point, the quantum mechanics. And to understand why we need each layer of abstraction, we have to understand what's problematic about everything underneath. So, what is the problem that quantum mechanics tries to approach? As we will see, this problem is so severe that simulating even small fluid systems on a quantum level is practically impossible. Okay, to see what's going on, we have to look at fundamental properties of nature. It ultimately boils down to how we think about measuring. For a macroscopic object, like this ball for instance, tracking its path or trajectory is an easy task. You just look at it, or use any other device that looks for you. The problem is, how do you track the path of smaller things, like an elementary particle? This could be an electron that moves around the nucleus of a hydrogen atom, for instance. You have to rethink what looking means. Let's build an experiment. Here we use a laser to shoot photons towards the atom, which itself is placed in an electric field. A photon may then kick the electron out of the electrostatic potential well that surrounds the atom, and when that happens, the electron is accelerated by the electric field to the right side, where its localized influence is detected. Now the details are not important here, but if this experiment is performed in the right way, it is possible to gain information about the original location of electrons within an atom. This is awesome! Seeing where electrons were in an atom. And when that happens, the electron is accelerated by the electric field to the right. We have to look at fundamental properties of nature. It ultimately boils down to how we think about measuring. For a macroscopic object, like this ball for instance, tracking its path or trajectory is an easy task. You just look at it, or use any other device that looks for you. The problem is, how do you track the path of smaller things, like an elementary particle? This could be an electron that moves around the nucleus of a hydrogen atom, for instance. You have to rethink what looking means. Let's build an experiment. Here we use a laser to shoot photons towards the atom, which itself is placed in an electric field. A photon may then kick the electron out of the electrostatic potential well that surrounds the atom, and when that happens, the electron is accelerated by the electric field to the right side, where its localized influence is detected. Now the details are not important here, but if this experiment is performed in the right way, it is possible to gain information about the original location of electrons within an atom. This is awesome! Seeing where electrons were in an atom, although by doing so, we change the electron's future significantly. In this sense, looking really means interacting. The specimen and the measuring device, electron and photon, are simply closer on the energy scale compared to any macroscopic. Localized influence is detected. Now the details are not important here, but if this experiment is performed in the right way, it is possible to gain information about the original location of electrons within an atom. This is awesome! Seeing where electrons were in an atom, although by doing so, we change the electron's future significantly. In this sense, looking really means interacting. The specimen and the measuring device, electron and photon, are simply closer on the energy scale compared to any macroscopic composition, so while you measure, you exert influence. Even if you use an experiment that does not rip the atom apart, we have to feel the electron in one way or another. So, practically, tracking an undisturbed trajectory of such small things appears impossible. Unfortunately, there's an even more fundamental limit about how certain one can ever be in terms of location and momentum of a particle, regardless of the measurement process, the Heisenberg uncertainty principle. So, even theoretically, talking about trajectories of such small things loses meaning. What does not lose meaning, however, is averaging many observations to yield a different kind of information, a probabilistic perspective. Because what makes sense nonetheless is to think about how likely it would be to detect an electron in a certain region of the atom. And depending on properties such as the electron energy or strength of the electric field, these probability distributions come in many different shapes. If there are multiple electrons around an atom, the picture is even more complicated since electron motion is correlated. So a true multi-electron probability distribution is not simply a composition of the single electron shapes, although it can be approximated by using them as a starting point. Either way, the result is always a probability distribution. The next peculiar thing about these small elementary particles is they behave not only particle-like, which means there's an integer number of them, and once measured you observe the impact at a certain distinct location, but they also behave wave-like, meaning they go around corners and superimpose, diffract and interfere, as long as you do not observe them. In this series, I don't want to focus on why nature has chosen to behave this way, but what it means for us as we want to derive models up on this basis. After all, we want to study fluid dynamics, but first we have to get there. So, to make sense of these probabilities and wave-like properties, some people decided to develop a mathematical tool that reflects this indeterminate nature they see in all their experiments in its core. And this tool is called quantum mechanics. The core of the approach relies on two mathematical objects: a wave function that contains information about the states of all considered particles, and an evolution equation, the Schrödinger equation, that works on the wave function and tells us how it changes with time. From the new wave function you can then derive the probabilities again. And this is the same kind of probability we talked about before. It tells us how likely it is to detect a particle in a certain region of space. We have a model for what we see in our measurements. The exact form of the evolution equation is here irrelevant. It is the underlying concept that is problematic. What we are really concerned about is how computationally expensive it would be to perform such calculations for a given volume of our fluid. And in that regard, we only need to know that it takes a certain amount of time to perform the evolution operation. So let's build some simulations. For our single particle here, the wave function assigns a complex number to each point in this two-dimensional space. The evolution equation now takes all these numbers and a problem-dependent term that specifies the rules of evolution, the Hamiltonian, and advances these numbers continuously and deterministically along time. So the same initial wave function will always give the same evolution. We can now represent the infinite number of these points and time steps by a finite number of values that a computer can handle. We will talk about such spatial and temporal discretizations later in more detail. For now, let's just assume we restrict our view to a subregion of space and subdivide the field to have 1,000 sections along each side. This means each of these cells stores a single complex number, and Erwin here has to figure out how 1,000,000 complex numbers change, since each of these numbers represents a part of the particle's wave function. It can be everywhere, and we need to account for that. 1,000,000, just for one particle to move through a tiny portion of space. You may think the problem is now simply that we need too many of these cells to fill up the fluid volume, but it gets even worse, by orders of magnitude. Look at this. If you look at only one slice of our 2D plane, we cannot explain why the wave suddenly behaves differently compared to a particle that lives in one dimension. We don't see the walls in this slice. This influence has to be provided by neighboring slices. Likewise, if you look at only one cell, we have absolutely no idea why it does what it does. Everything is coupled through the evolution of one underlying wave function, and neighboring cells have to tell us what's going on over there. This dependence on one wave function is even more striking when we think about multiple particles. These two particles live in one dimension. They move towards each other, and in general, their motion depends on each other. And you can now quantify how likely it is that particle 1 is detected in this arbitrarily selected region, while particle 2 is detected in that region. This gives a joint probability. Since each particle's individual probability distributions cover all of 1D space, we need more degrees of freedom, more space to store the joint information. So there's still only one wave function that gives rise to the probabilities, but it lives in 2 dimensions. Both particles are then represented by the joint probability of detecting one particle in a certain region, while the other particle is detected somewhere else. You can still describe the probability of a particle alone by extending the range of detection along the other particle's axis to plus minus infinity. Again, the wave function describes a joint probability and tells you something about a combined measurement outcome. And by considering every possible position of the other particle, you get the individual particle probabilities. In this sense, both particles' probabilities eventually appear as so-called marginal probabilities by looking along different directions, each giving a unique perspective on the same high-dimensional wave function. So far we have a pure mathematical framework that we should equip with different properties to reflect known physical behavior. For instance, some particles repel each other, and by using interparticle potentials we can force the wave function to account for that. We will learn more about potentials later in this part. A particularly important property is that particles of the same kind are indistinguishable. They can't be physically labeled. So you don't detect electron 1 and electron 2, you detect one of the electrons and the other one. By implementing symmetries, you see that both electrons can be detected in switched positions, making this model useful for physics. So after all, while the physical 1D space may be discretized using just 1,000 cells, the 2D wave function for both particles requires, in the worst case without symmetries, 1,000,000 cells. If we have two particles in a 2D physical space, the wave function lives in 4D space. As much as this may be confusing at first, it is also a challenging task for Erwin here. He has now to work on 1,000,000 times 1,000,000 cells for two particles. So far, it seems we are simply lost in computational complexity. Okay, there will be shortcuts and approximations, but then again, throw 5 more particles in, each bringing its own set of additional dimensions along. Oh, and we do live in 3 dimensions, and some particles have additional properties such as spin, so the probability space is even larger. You see where I'm going with this. It gets impossible really quickly, at least when using conventional computers. Okay, this is a result we expected, since we knew from the beginning that it will be impossible to simulate fluids quantum mechanically, but I'm always curious about where everything comes from, and really seeing why something is a bad idea is not a bad idea. So we need to do better. We need to construct a surrogate model that represents the essential physical properties while being way faster to solve. And whenever you want to simplify, you can usually select among a variety of approaches. One popular way to reduce information builds on the fact that dynamical systems often evolve in specific patterns. To demonstrate this, we look at this one-dimensional particle here represented by its wave function components. To keep it around the center of the scene, we add a so-called potential that pushes it back the further it goes off-center. It is nothing special, it works a bit like a marble in a bowl, kind of. We discuss potentials in a minute when we focus on modeling interatomic behavior. Anyway, this is the kind of instruction we must tell the evolution equation via the Hamiltonian, which basically keeps track of the total energy of the system, and potential energy is certainly part of it. So, as we start the simulation, Erwin, please. We see the wave function, and so the probability wiggles around, and a certain repetitiveness appears. And here's a clue. It is possible to construct a few specific wave function shapes, or standing waves, that combined in the right way approximate the true evolution astonishingly accurate. So instead of evolving 1,000 individual cells, we only evolve a few individual scaling factors of these superimposed shapes, also called mode shapes. And in our case, due to the linear form of the evolution equation, these scaling factors are even simpler to compute. So once you have these shapes, you save a lot of computational time here. The name standing wave simply reflects that the probability which determines the measurement outcome does not change, although the underlying wave function components do oscillate with a certain frequency. This is possible if each individual complex number happens to evolve along a circle in the complex plane. In this way, the probability as the absolute square of the wave function value stays constant. And the oscillation frequency of this rotation will be super important later on. What's good is, the choice of shapes and their number gives you the freedom to adjust the accuracy of the reduced model to your needs. And this approach is not limited to quantum mechanics. It is a general mathematical tool sometimes called model order reduction, but it is known by many names, and it is a huge topic on its own, and we will explore and apply it many times in the future. But right now, it is not what we need. It does provide the features for a drastic reduction and is often applied with great success. That's why I had to mention it here. But it does not change what you are modeling. Here it means you are still concerned with wave functions and probabilities, and representing a gazillion fluid cells by a trillion modes does not really help for our goal. In fact, computing these shapes for higher dimensional systems in the first place is complicated on its own. Right now, we need a different kind of reduction. We need a change of the underlying paradigm. We need molecular dynamics. You see, so far we evolved all values of the wave function in a possibly large space, simply because the nature of joint probabilities left us no other choice. But what if we could ignore the wave-like properties and probabilities? What if particles could be distinctly located and we...
Здравствуйте, в эфире новости Удмуртии, в студии Марины Симоновой. Смотрите в этом выпуске. В поликлиниках республики возобновилась прививочная кампания от гриппа. Республика получила партию вакцины. На страже закона и порядка. Сотрудники органов внутренних дел принимают поздравления с профессиональным праздником. И медведи уходят на зимнюю спячку. Как им помогают подготовиться пережить зиму экологи, расскажем. В Удмуртии могут возобновить углубленную диспансеризацию. Об этом Александр Бричалов сообщил во время прямого эфира. Медицинское обследование пациентов, переболевших новой коронавирусной инфекцией, может начаться уже с 22. Особое внимание врачи будут уделять людям с хроническими заболеваниями, сердечно-сосудистой, дыхательной.
Hello, my name is Dr. Jacob Graham, and in this video we will learn how to compose 4-to-1 counterpoint. This is the most extreme rhythmic proportion in traditional species counterpoint, with one melody moving 4 times as fast as the other. This makes it very difficult to achieve an equality of voices, because the faster melody is obviously going to be way more attention-getting. Finding ways to solve this basic problem is the most important lesson to learn from our 4-to-1 exercises. Four-to-one exercises are written in quadruple meter, usually 4 quarter notes in the counterpoint melody against each whole note in the given melody. The first beat of each measure is the downbeat, and just like in all the previous exercises, only consonant harmonic intervals are permitted on the downbeat. Of the other 3 beats, beats 2,